Hi there. So in this video, we're going to talk about the equation of a plane in space. So if you haven't got the idea about what a plane is down, hopefully you do, but it's just a flat something in space. Okay, so I like to use hands-on things to try to understand and demonstrate things. And so we can be talking about, planes being tilted in all different directions. And so I usually get a piece of cardboard out just so it stays rigid to help me with that. Okay, and so let's think about a line real quick and go back over that and then talk about what's going to be slightly different whenever we try to describe a plane in space. Okay, so if you remember with the equation of a line in space, we need a point that's on the line and a parallel vector, okay? Now, we got to remind ourselves why we need each one of those. So remember, what does the point do? It fixes the location, all right? And so that's the reason for that point. And we'll see with the plane, it should be obvious that we need a point that'll fix the location. But what does the parallel vector do for us? If you remember, that gives us the direction, okay, like that. All right, so now let's look at this, okay? And so again, to get the equation of a plane, remember whenever we're talking about getting an equation for and understanding what we need things that will uniquely determine that plane. So this is going to be my plane and this is going to be a vector, okay? And so it's tempting to think with the plane that you would also need a parallel vector. Okay, and so the idea is if I say that a plane has to be parallel to this vector, let me move it over here so I can do something. All right, we can see that, but does that uniquely determine the plane? You might want to pause and think about that. Does this plane fix? Is there any other plane that's possible that has this parallel vector in it? And see, I can rotate that plane around. I could go 360 degrees. I just don't want you to see that I have printing on the other side of my cardboard, but I could rotate that thing 360 degrees around. So to say that I have a parallel vector, it won't uniquely determine that plane. There's infinitely many planes that have that parallel vector that are all still fixed in that same location. Okay, and so that's the problem with trying to use a parallel vector. So maybe pause and stop and think about what could give you the direction instead. I'll give you a hint, it is a vector, but that vector can't be parallel. All right, and if you think about it, you might be able to get to that pretty easily. But say that I had this plane, it needs to pass through this point, so it's somewhere in here, okay? But say I tell you that a vector has to be perpendicular to it, orthogonal to it, like that, okay? Are there any other planes possible? Let me draw it like this so you can see that perpendicularly better. All right, are there any other planes possible that go through that point and have this orthogonal or perpendicular vector? And the answer is no. There's only one plane. I can't see if I try to move it, that vector is no longer orthogonal. Okay, like that. And if I move my vector, then I got to move the plane. And so there's only one plane that's going to be determined, as long as I fix the location too, and then say I have an orthogonal vector. Okay, now what we're going to see is a new term. When an orthogonal, remember this is a surface, okay, it's two-dimensional, and so this is a surface, and whenever we talk about a vector that's perpendicular to a surface, we call that a normal vector, all right, like that. And normal vectors are very important. Notice with a plane is flat, so no matter where I put that vector, I'm going to get the same orthogonal. It's going to be orthogonal no matter where I put it, okay? But if we think about a surface, let me get something a little more pliable, all right? So that has some math on it. Let me grab something that's blank, at least on one side, okay? So we can think about a surface as just being a piece of paper that's been deformed in some way. Notice on a regular surface, as you go from point to point, that normal vector is going to change. Those end up being important to help describe properties of surfaces that we probably won't get into in this course, but normal vectors are actually really important in 3D geometry. Okay, and so just to summarize that now, to describe, some object, that basically if we get the equation, we can describe everything we need about it. So whenever I say describe, I'm talking about get the equation. For a plane, you need two things. Remember, like I talked about in the last video, always focus on what you need when you're trying to get an equation for something. So the two things you need is you need a point in the plane or on the plane and a normal vector. And we usually use the letter N to denote normal vectors. Okay, and so a normal vector, and just remember, a normal vector is a vector that's orthogonal to the plane and to a surface in general. Okay, now let's talk about how we actually get that equation. Okay, so just like with lines, there's going to be a vector form of the equation and a scalar form. All right, and so here's how to derive the vector equation for a plane. So remember, to do this, we need to be given a point that's on the plane that we'll call P naught and a normal vector n. So n is orthogonal to the plane. All right, and now I'm going to show you how we can derive that. Okay, so right here I have the coordinate plane, and I've specified a point P that I want to be on that plane. So the first thing I need to do is specify the direction by giving a normal vector, n, right there. Okay, now notice n's not really easy to see. I could drag my screen a little bit better, but remember, we also have liberty to draw a vector wherever we want. So instead of drawing it starting at the origin, why don't we draw it starting at P naught instead? Oops. And so so I get that picture right there. All right, so I don't know why that is way over there, but anyway, there's our normal vector n. Okay, now so now what's next? This is what takes a little bit to absorb. Hopefully my demonstration earlier helped, but those two things, the point and the normal vector, completely determine this plane right here. There's no other plane that passes through that point and has that normal vector. Okay, and just to help you see that those things are normal to each other, you can see pretty plainly right there that they're form a right angle, right? Okay, and so anyway, so all right. Now remember, to get the equation of any kind of object, we need to be able to describe a general point on that plane. So I can take any point that's on that plane, all right, and I'm going to call that P, and so so you can see that it's called the point P there. And I'll show you in a minute this will apply for any point on that plane. And there's nothing special about the point P right there. Okay, it's just a general point on the plane. All right, now being points, remember that we can form their position vectors. So that's the vector that extends from the origin to the point. And so since my first point is P naught, I would call its position vector R naught. So that vector right there is R naught. All right, and then likewise, I can draw the position vector for P, and so I would just call that vector R since there's no subscript on it. Okay, and remember, the idea is to be able to get some kind of equation for that position vector R. All right, now if you remember from the last video on lines, or in general, we want to form the vector that starts at P naught and extends to P. So that vector right there, okay? Now, if you remember, we can actually say what that vector is in terms of those two position vectors. You might just remember from the last video, or if you think about the forming the parallelogram between the two position vectors, or determined by the two position vectors, that vector right there is going to be the difference of R minus R naught, okay? And so we get that vector. Now, the key thing to notice here is the relationship between the normal vector and that R minus R naught. You might be able to see it just from that picture alone right there, but if I kind of straighten it out, you can really see it, that N and R minus R naught, are orthogonal to each other, and so that would say that their dot product is equal to 0, and that ends up being a key property. Sorry, my graphics went a little weird, but N dotted with R minus R naught is going to be equal to 0. One thing that I just almost forgot to show you is it doesn't matter which point on that plane we pick. So if I move P over here, notice that those two vectors are still orthogonal to each other, like that. And so I can move that point P anywhere on the plane I want to. Let's move it over here. Now that kind of looks like it, but to really convince yourself, you need to rotate things. So hopefully you can see anywhere where I put that point on the plane, we're still going to get this relationship that the normal vector dotted with that difference vector is going to be equal to 0. So believe it or not, that's actually a working definition for a For the equation of a plane, it's called the vector form, just like we had a vector form of a line. That seems very abstract, and it's hard to see where things are going on. So to try to start clearing it up a little bit more, you could say n. Remember, r is the position vector for p, so it just has coordinates x, y, and z, like that. And then r naught is the position vector for our given point, so it has coordinates x naught, y naught, and z naught, like that. And then that's equal to 0. And right here I'm just subtracting two vectors. So it starts getting it a little bit more foreseeable that you're dotting in with this vector x minus x naught, comma y minus y naught, comma z minus z naught. That's still kind of hard to see how things work and so on, but that could be a form of the vector form equation of the line. But now what we're going to do on the next slide is we're actually going to write out what this dot product looks like and get a more familiar version of the equation of a plane. So yeah, let's see how to go from the vector form to what's called either the scalar or general form of the equation of a line. So where we just left off is we had n dotted with the vector x minus x naught, comma y minus y naught, comma z minus z naught, right? Like that, and that's equal to 0. Okay, so now I just perform that dot product. So if you remember, so we could think about n having coordinates n1, n2, and n3, like that. Okay, so if I go and write out what that dot product is, I would multiply the first component of n times the first component of that difference vector, so it would be x minus x naught. Okay, and then plus I multiply the second component of n times the second component of the difference vector, and remember I add everything together, and then plus the third component of n times the third component of the difference vector. Okay, like that. Now what's going to happen, this is the form that we'll start out with. Okay, remember we're going to be given n and the point p naught, so I can fill all of these things in. Okay, now I said we're going to be given, for the first problem or two we'll be given all those, but then we'll have to figure some of that stuff out. But after we've done some work, at least we'll know what n is, and we'll know what these three coordinates are of our given point. So we'll just fill those in here like that. All right, but this is still, sometimes we keep it in this form, and it just kind of depends on what you're doing, and I'll explain as we go through the course. Different times we keep it in this form and not. But whenever you're just talking about equations of planes, we usually go ahead and multiply things out. Okay, and so then we multiply that out. Okay, like that, and after you do that, you end up with a very linear looking equation. Okay, and so it results in an equation of the form. Okay, so think about what I'm talking about. We're going to be multiplying things out, okay, like that. They're all going to be equal to 0. So what you're going to have is you're going to have this n1 times x and n2 times y and n3 times z. Just to show you this general form, I'm going to call, instead of using n1, n2, and n3, I'm going to use a, b, and c. So I'm going to have ax plus by plus cz, okay, and then notice I would have n1 times x naught. That's just a number, because these are numbers that I'm filling in. And we're subtracting, don't worry about that. Okay, but notice whenever I multiply here, I'm just going to get a number. Same thing here and same thing here. So those are just going to be three numbers that combine. So we'll just call that number d equal to 0. Okay, like that. And what this is called right here, this is called the general equation of a plane. All right, like that. All right, so there's a few things here, and I know it's kind of a lot, but to start getting the equations, after we maybe do some work, we'll have n and we'll have p naught. Okay, so we'll fill in numbers to this form right here. Okay, but then to actually get an answer, we'll want to multiply out and add those numbers, combine those numbers like that. So you'll end up with this. Now the thing is, especially later in the course, we'll be talking about some plane. So we might be talking about some plane 3x plus 2y minus 4z plus 1 equal to 0, like that. Make sure you realize you can find the normal vector to that plane, because this A, B, and C were just the components of n, all right? And so n, in this case, would be the vector 3, 2, -4. Now, as far as what other point is on the plane, what other points are on the plane, you got to do some thinking about that. And I'll point that out in a minute, but you might want to pause right now, because I'm surprised at how often people forget how you could get points on that plane just from the, this equation right here. Okay, so what we're going to do is some examples now. Okay, and I'm also going to talk about getting other points on the plane too. I should have written that in the directions, but I forgot. So anyway, we're gonna have some kind of plane described, and we want to get its equation in general form. Okay, so number one is going to be basic. It's just practicing getting that form down. Okay, so it's saying, you know, since I said a plane is described, I didn't write it, but we're talking about the plane that passes through the point 4, 2, -1 with the normal vector 3, 2, -2, 5. Now, especially once you start combining things, or by the time you get to a test, or just in general, okay, in general, you know, the idea is you want the equation of a plane, right, like that. So it's the equation of some object. So focus on what you need. All right, and this one's straightforward, but in general, problems get tricky, and so focus on your work on what you need. And to get the equation of a plane, you need a point, and you need a normal vector. Okay, now notice they're both given to us here. So the point in general we call x naught, y naught, and z naught, like that. And so that would be the point 4, 2, -1, like that. And then the normal vector we denote n, and so it's going to be the vector 3, -2, 5. Okay, like that. So now you can go straight to that basic form. If I were to ask you for the vector form of the line, you could start even more basic. But if you're just trying to get the general form, the basic form is just n1 times x minus x naught plus n2 times y minus y naught plus n3 times z minus z naught equal to 0. Don't forget that equal to 0. People often forget to write the equal to 0. Okay, and so funny side story about that equal to 0. That just made me panic. I went back to the slides to make sure I remembered to write it. It's just easily to forget it. So remember, you're getting the equation of something, so you should have an equation, and equals is what makes something an equation. Okay, anyway, so what are these numbers? So here's my normal vector n. So in terms of that n1, n2, n3 I keep writing, that's these numbers right here. And then, like I said, the x naught, y naught, and z naught are the coordinates of this point. So this problem's straightforward. We're just plugging things in. And so we have n1, which is 3, times x minus x naught, which would be 4, and then plus -2 times, and if you realize that's going to become a minus, don't feel like you have to write it that way. So then we have y minus y naught, which is 2, like that, and then plus n3, which is 5, and then z minus -1. That's all equal to 0. Okay, and so for some reason I have this thing over here. Okay, and so anyway, now, you know, I got a little bit of cleaning up to do. That's the advantage to seeing it and just writing it the correct way. But so we got -2 times y minus 2 plus 5 times z plus 1. Okay, and like I say, stopping here is advantageous often, especially once we start doing calculus on planes, because of those differences. If we're talking about the difference in coordinates, remember that's a differential whenever you have independent variables. We'll worry about that later though. Okay, for now let's just go all the way to the general form. And so I just multiply everything out. So I get 3x minus 12 minus 2y plus 4 plus 5z plus 5 equal to 0. And see, now it might make more sense what I was talking about a minute ago. So I have the 3x and the minus 2y and the plus 5z. Okay, but see, notice that I have these three numbers right here that I could combine. So I see that those are positive 9 and then minus 12, so I end up getting minus 3. All right, like that. Okay, and so there is the equation of my plane. Okay, now a good question, and this connects with a lot of things we've been talking about even from day one. How do I get another point on that plane? Okay, I know one point that's on it. How do I get another point? Okay, and so the idea is you got to remember we're talking about a plane. That's a two-dimensional object. And so what have we said? For a two-dimensional object, we have 2 degrees of freedom. DF is a typical abbreviation. What does that mean? That means there's 2 independent variables. Okay, what does it mean to be independent? An independent variable is that you can make up any value you want for those two variables. So it doesn't matter which 2 you pick. Okay, so I could say like x is equal to 1 and y is equal to, I could use 1 too, but I'm gonna say y is equal to 2. And you could make one or both equal to 0 to get an easy point too. All right, so what would happen if I do that? 3 times 1, 3x, minus 2y plus 5z minus 3 is equal to 0. Okay, so I have 3 minus 4 plus 5z is equal, minus 3, sorry, minus 3 is equal to 0. So I have 5z minus 1 minus 3 is minus 4 equal to 0. And so z is equal to 4/5. Like that. Now don't stop there. I'm asking for a point. And so what point did I just realize was on the plane? The point 1, 2, 4/5. Like that. One more quick note too. So we think we have the answer here, but you can see there's a lot of areas to make little silly mistakes. And so how could you check that this is actually correct? Well, what's supposed to be true about this plane? It's supposed to have this normal vector. Remember, the normal vector shows up as the coefficients on x, y, and z. So let's check that. 3, -2, 5. So this does have the normal vector. What else should be true? It should pass through this point 4, 2, -1. What does that mean? If I plug in x equal 4, y equal 2, and z equals -1, this should give me a true statement, i.e. I should get 0 on the left side. Okay, so what do I have? I have 3 times 4, which is 12. Minus 2 times 2 is minus 4, so I have 8 now. And then 5 times -1 is -5, so that gives me 3 now. That all this combines to 3. Minus 3 equals 0. So I know I'm correct, and so I could check that off and move on. One quick note before moving on is, what's a way I could draw this plane? How could I get that plane drawn? I could draw the normal vector and draw the coming from the point that I was given, and then try to kind of get a picture there. That can be kind of hard. Let me show you one basic way that people will draw planes here, and I was hiding something from you here. All right, I would have forgotten those 2 points if I didn't just do that. So anyway, there's my 2 points that I already know that are on the plane. Okay, well, just like with a line, the basic way to determine a line is with 2 points. The basic way to determine a plane is with 3 points. So I could get a third point. And let me show you something you can do too. I was just trying to show you that general thing. I remember I have 2 degrees of freedom. So I could I could make things really easy on myself, and I could pick y equals 0 and z equals 0. Like that. Whenever I do that, my equation is going to become 3x minus 3 is equal to 0. And so I'm going to get x is equal to 1. So that tells me that this point is the point 1, 1, 0. Okay, so now I have 3 points, and so I can plot those 3 points. All right, and this is just kind of the way I do it. One other thing to mention too is what would we call this? This is the place where that plane is hitting the x-axis, so that is an x-intercept. And you can see the idea of finding intercepts works the same in 3 dimensions as 2 dimensions. If you're trying to find an intercept, you can set the other 2 coordinates equal to 0. And that's how some people will draw a plane, at least get a picture of a plane, is they'll find the other 2 intercepts as well. So let me show you 2 ways. Okay, since we were given a point and we found another point, I could just try to draw it from these 3. And what I usually do is I just draw a little triangle and that usually gives enough information where you can at least get an idea about what that plane looks like. All right, so let's see, I have the point 4, 2, -1. Okay, so it's that point is going to be kind of right in here, that general idea. Okay, and then I have the point 1, 2, 4 fifths. So 1, 2, 4 fifths. So just about right here, like that. And then I have the point 1, 0, 0 right there. Okay, I mean, and this isn't ideal, but if I draw the triangle connecting those 3 points, then you can get an idea that that plane is roughly looking like this right here. Okay, and a lot of times I'll just draw the triangle just to give myself an idea. All right, now the reason we did it this way is that we already knew 2 points. Okay, but if you're starting from scratch and you don't know much, you can just find the intercepts. And so we already found the x-intercept, and so for the y-intercept, then we're setting x equal to 0 and z equal to 0. That's going to give me -2y minus 3 equals 0, like that. And so we're going to get y is equal to -3/2. Okay, so that's going to be 0, -3/2, comma 0. And then for the z-intercept, okay, then we're going to have x equal to 0 and y equal to 0, like that. And so we would have 5z minus 3 is equal to 0. And so I could set z, or that makes z equals 3 fifths. And so we get the point 0, 0, 3 fifths, like that. Okay, and so now I can just go back. We're basically going to get the same picture. It might look slightly different. Just, let's see, graphing intercepts is slightly easier. Okay, like that. And so what's the idea here? We have 1, 0, 0, and then we have -3/2 for my y-intercept. So my first point is here, my second point is here, and then 3 fifths on my z-axis, so not very high up right there. So that's getting a picture of that plane using the intercepts. That way, a lot of times you can see that inclination a little bit better, like that. And then again, it's still that idea that you have that plane kind of tilted, going down toward you in the screen. Okay, just one thing to be aware of: sometimes people get stuck because not every plane has all 3 intercepts. So remember, the general idea is to be able to get 3 points, and then you can draw this triangle at least to get an idea of what it looks like. Alright, so basically, because you can always draw a plane given 3 points, the most common situation to need the equation of a plane is whenever you know 3 points. In most cases, that uniquely determines a plane. There is a special exception I'll point out at the end of this slide. But anyway, we're looking for the plane that passes through those 3 points right there. Okay, so we can get an idea, and this will help us figure out how to do it. Okay, I'm just going to kind of rough in where those things would go. So 3, 2, 5, so about right in there. All right, so our first point would be somewhere around in here, and then 0, 2, 0, that would be here, and then -1, oops, I keep doing that, -1, 4, 1, so right around in here would be that third one. So our plane, at least a triangle that's in that plane, kind of looks like this, and this triangle is going to help us. Okay, so we're back to getting the equation of a plane. Okay, and this is where it's really important to always focus on what you want. You want the equation of a plane. Okay, so what do we need? We need a point. That part's nice because we have 3 points. We can just pick which one. Okay, and then we need a normal vector. Okay, so the point you get to pick. Always make things as easy on yourself as possible. So I'm going to pick that simplest looking point, 0, 2, 0. So again, just remember that's our x naught, y naught, and our z naught. Okay, and so now the question is, how do we get the normal vector? Okay, that's the harder part of this. So we need you got to remember what a normal vector is. It's a vector that's perpendicular or orthogonal to the plane. So here's a picture of my plane, at least a triangle in it, okay? But since that triangle is, this might help you, since that triangle's in the plane, I need a vector that's orthogonal to that triangle, okay? If it's orthogonal to that triangle, it'll also be orthogonal to the plane. So if you're not seeing it, you might want to pause a minute and think about how you could get that orthogonal vector. Okay, but the idea here is that I have this triangle. So remember, we were using triangles to get orthogonal things in a previous video. We could use the cross product if I form some vectors. So I need to form some vectors here. And so the idea is you just want to form any two vectors that have the same tail. All right, and so it doesn't matter which two, but for my tail, I like to use the simplest point possible. So I'm going to use that 0, 2, 0 again for the same purpose. And so I'm going to form the vector that goes from this point to this point, and the vector that goes from this point to this point. All right, and so let's label some points in here just to help us. So let's call this P1, or let's see, we're using that for P naught. So let's call that P naught. Let's call this P1, and let's call this P2. Okay, like that. All right, and so what I need to do here for my normal vector is form the vector P naught to P1, form the vector from P naught to P2, like that. And how do I get an orthogonal vector from them? I take their cross product. Okay, and so I'm going to move it. I might move a little bit fast here, but I'm not going to move too fast because I don't want to make a mistake. And so we're going, let's see, P2 is actually the 3, 2, 5. Okay, if you remember, P1 is the negative 1, 4, 1. All right, and so if I'm doing P naught to P1, I do coordinates of this minus coordinates of that. And so I'm going to have negative 1, 2, 1. Okay, and then P naught to P2, I want to do coordinates of this minus coordinates of that. So what do we get there? We get 3, 0, 5. Zeros and cross products are nice. All right, so you might want to make sure you can get that. Whenever I do them by hand, I always write the second vector underneath it. I don't use the determinant rule. I noticed that pattern a while back, and I always use that. So in my first coordinate, though, I'm going to get 10 minus 0. All right, and again, if you do it a different way, just pause and see if you can get the same thing. So in my second coordinate, I'm going to get 3 minus negative 5. And then in my third coordinate, I'm going to get 0 minus 6. Okay, like that. And so if I go and simplify things, I have 10. And then I have 3 plus 5, that's 8. And then I have 0 minus 6, which is negative 6. So I could use this as my normal vector right here. Okay, that's fine, because all we need is any vector that's orthogonal to the plane, and this vector is. Okay, but notice that a 2 factors out of that. And see, this is a simpler vector. And so, especially with planes, you really, you don't have to, but you really want to get any common factors out of the way that you can. And so, what I'm going to do is instead of using that original normal vector, I'm going to use that simpler one, 5, 4, negative 3. Okay, if you're having trouble seeing that, the answer that we got, the 5, 4, negative 3, it's a vector that points kind of out like this. All right, I'm sorry, the original vector I got was the 10, 8, negative 6, but it's a really long vector. Okay, so it extends way out here. All right, and so what I did is I just took a vector half the length right there. That's my new n. And notice all I did was change the length. I didn't change the direction, so that vector is still orthogonal to the plane. Okay, now let's just finish this. And so as far as the equation goes, we got n1 times x minus x naught plus n2 times y minus y naught plus n3 times z minus z naught equal to 0. Okay, like that. And so I just fill in 5 times x minus 0 plus 4 times x minus 2, or y minus 2, sorry about that. And then plus negative 3 times z minus 0 equal to 0. So I go and multiply this out. Those zeros make this a little bit nicer. That's why you should use the simplest point that you can. So we have 5x plus 4y minus 8, and then minus 3z equal to 0. All right, and just one small thing to clean it up. And so we just need to move that 8 out of the way. Okay, and so I actually had to edit that because I forgot to write the minus 8 the first time. I almost did it again. All right, so there's our answer right there. Okay, now one thing too, if you had used that more general form of n, basically all these numbers would have been doubled. Okay, and so you would have had 10x plus 8y blah 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 equal to 0. But since everything divides by 2, you would want to divide both sides by 2 to get it in that form right there. So you don't want extra factors in your equation. You want as basic as you can. All right, and then also, how would you check this just to make sure? To actually check this, what's supposed to be true about this plane right here is it's supposed to pass through all three of these points. And so you should plug this point in for x, y, and z, make sure that everything adds up to 0, then plug in 0 to 0, and make sure that everything adds up to 0, and then plug in negative 1 for 1. Okay, I'm going to save it some time and not do that, but that's how you would actually check that. Okay, so I'm going to leave it there. You know, the key thing is, what are we doing here? We're finding the equation of the plane. So once you get into homework and on the test, first of all, you're finding the equation of something. So anytime you're finding the equation of something, focus on what you need to get that equation. All right, and now that we're doing planes, what do you need? You need a point on the plane and a normal vector. And so make sure in trickier problems to keep focused on that. And if you find yourself doing work that is not leading anywhere, you're not sure where that's leading, just stop and then try to refocus yourself. Okay, so anyway, I hope that helps. Let me know if you have questions, and I wish you the best.